This is my trigonometry course. Today we're going to learn a few more identities, and these are going to be some of the last equations that we have to learn in this course. So first we'll learn the opposite angle identities. If you have some number x, then the opposite of x is negative x. And if you have some number negative x, the opposite of negative x is x. So it just means that you're going to change the sign. So what this means is that if you have the sign of negative theta, then the negative can just come out and go right in front of the trigonometric function, meaning we have the function multiplied by -1. So you're going to want to get a picture of these opposite angle identities. And as you can see, with cosine and secant, the negative really just disappears. The cosine or secant of a negative angle is equal to the cosine or secant of the corresponding opposite angle, the positive angle. So let's talk about why that is true. Let's say you have some angle theta. Now this works for any angle. It can work for acute angles or obtuse angles or reflex, but we're just going to use an acute angle as an example, and we'll call the opposite side y, the adjacent side x, and the hypotenuse r. So sine theta is y over r, opposite over hypotenuse. Now let's draw a negative angle. Now the angle measure is the same, except in standard position we're rotating clockwise, so we're going to rotate down, so this is going to be negative theta. If we assume that the theta value is positive, which it obviously is because it's going in the counterclockwise direction, then negative theta would rotate in the clockwise direction. And now you can see that sine of the negative angle is equal to negative y over r, because now the triangle is going down and this side length is below the x-axis, so it's going to be negative y. That's the only difference. So that said, it is not true that sine of a negative angle is equal to the sine of the corresponding positive angle. This is not true. But we can modify the equation slightly by writing a negative symbol. You see that purple negative symbol there. We can write a negative, and that will change the equation so that it is true. Sine negative theta is not equal to sine theta, but sine negative theta is equal to negative sine theta. And here's some other examples. With cosine, as I mentioned, the negative just goes away. Here's a positive theta value in standard position, positive angle, and now I'm using an obtuse angle just as an example. Again, this works for any angle you want, acute, obtuse, reflex. So cosine is negative x over r because the triangle is in the second quadrant. Now over here, let's draw the exact same angle measure, except it's going to be negative theta. So it's going to rotate in the clockwise direction. Well, now when we find the cosine of the negative angle, it's the exact same value, negative x over r. So we get the same expression. So the cosine of a negative angle is equal to the cosine of a positive angle. Or another way to say it is the cosine of an angle is equal to the cosine of the opposite angle. And here's another example down here. We don't have to keep going through these. Most students, to be honest with you, just memorize these formulas. They don't really think about these proofs. And these identities are not going to be used very often in the curriculum, but you will see them. It's a guarantee that you will see them at some point. And you may see them in proofs, but you're also going to see them in rare occasions in the actual math that you do in upper courses. So let's get some practice here. Again, I'm going to give you one more chance to take a picture of these identities with your phone. You're going to need these right in front of you as we do our practice problems. So we're going to do some more proofs. It says prove that the following equations are true by converting the left side to the right. So I'm going to prove that this is true by converting it to 1. The problem is cosine squared plus sine squared, that is equal to 1, but we don't have sine squared theta, we have sine squared negative theta. But that's okay. First I'm going to rewrite that expression, and you can use brackets if you want. So remember, this notation is very confusing with the exponent in the middle of the function, but this is really all that it means. You're just taking the sine function and you're squaring it. So I'm just rewriting it to avoid confusion. You don't have to rewrite it like that if you don't want to. So now we're going to use our identity. The cosine of negative theta is equal to negative sine theta. That is one of the opposite angle identities that we just learned. But notice that when you square negative sine theta, it just becomes, well, let's go ahead and write it out just so you can see exactly what is happening. Again, you don't have to write this out, but I just want to be absolutely clear what is happening. You're multiplying negative sine theta and negative sine theta, so it becomes positive sine squared theta plus cosine squared theta. And of course, now that's a Pythagorean identity. So we proved that the equation is true. So these problems are not meant to be tremendously difficult. They're just meant to familiarize you with these new identities that we're learning. These are equations that you need to have in your toolkit when it comes to trigonometry. If you don't have some familiarity with these identities, then it could cause problems in upper mathematics at some point. Okay, let's try number 2. So remember, the cosine of a negative angle is just cosine of the positive angle. It just goes away. And the same with secant. Secant of a negative angle, it just becomes secant of the positive angle. It's the same thing. You can just make those negatives disappear. Now again, if you object to that, here it is. These are the middle equations here. Those negatives will just go away. Cosine of a negative angle is just cosine of the positive angle. Secant of the negative angle is just secant of the positive angle. So now I'm going to change this to the old style division, and I'm then going to change secant to 1 over cosine. So that was a reciprocal identity. And now remember, when you divide, you just change to multiplication and you flip the divisor, and cosine A times cosine A times cosine A over 1 is cosine squared A. So we proved that that identity is true. Okay, so now we're going to go backwards. We have a negative cotangent theta, which is equal to cotangent negative theta. So let's go check our identities. See, negative cotangent theta is equal to cotangent negative theta. So I'm going to go right to left in this problem. So this here is equal to cotangent negative theta. And this here is also equal to cotangent negative theta. And so we have 1 cotangent negative theta plus 1 cotangent negative theta is 2 cotangent negative thetas. So there you go. Okay, let's do one more of these before you try one on your own. Again, with secant and cosine, the negatives inside the angle, they just disappear. So we're left with secant of the positive angle. And secant alpha minus secant alpha is 0, so we proved it. So I want you to try number 5. And when you come back, we'll do it together. Okay, we're back. So remember, with sine, the negative kind of just comes out of the function. And now negative sine x plus sine x is 0, and there you go. Okay, let's try number 6. Go ahead and attempt number 6. And when you come back, we'll do it together. Okay, we're back. So with tangent, the negative comes out, just like with sine. And I'm going to switch to the old division symbol. The fraction line can be interpreted as a division operation. And then I'm going to use a reciprocal identity, change cotangent to 1 over tangent beta. So that was a reciprocal identity. Then I'm going to follow the old division algorithm, change to multiplication and flip the divisor and then multiply, and we get negative tangent squared beta. So we did it. So if you got that one right, excellent. Go ahead and try number 7, and when you come back, we'll do it together. Okay, we're back. So again, with cosine, the negative kind of just disappears inside there. 2 apples plus 1 apple is 3 apples. So if you got that one right, perfect. Go ahead and try number 8, and when you come back, we'll do it together. Okay, we're back. So with cosine, the negatives come out. And just to be safe, we'll use parentheses. And a negative times a negative is a positive. And cosecant A times cosecant A is cosecant squared A. So if you look at your Pythagorean identities, you know that cosecant squared A is equal to 1 plus cotangent squared A. If you forgot that Pythagorean identity, that's okay. Remember, that's one of the 3 Pythagorean identities that we learned. So sorry if that last problem was kind of a curveball. Okay, so those were the opposite angle identities. So the reason we're leaving these, we left these identities towards the end of the course, is that, again, they're not used nearly as often as the the previous identities that we learned. So now we're going to learn complete rotation angles and half rotation angle identities, or complete rotation angle identities and half rotation angle identities. So notice that when you add or subtract 360, it doesn't change anything. So sine theta, ignore the pink curve and just look at the green theta. Sine theta is equal to the opposite over the hypotenuse. Is that right? Well, now let's take theta. You see this orange theta here, and now let's add 360. So what does that mean? It means we're going to start here. We're going to rotate theta degrees. You ready? We're rotating theta degrees. That's this theta here. We're rotating theta degrees. And then we're going to rotate 360 degrees from here all the way until we get to where we left off. So again, first we're going to rotate theta. Then we're going to start at that point and rotate 360 degrees all the way till we get right where we started there. So that is 360 plus theta. But notice that that's just a coterminal angle. We learned coterminal angles. So it doesn't change anything. Sine theta plus 360 is the same thing as sine theta. They're both the opposite side over the hypotenuse. Furthermore, if you subtract 360, you have a similar situation. So if you rotate theta degrees and then you subtract and go the other way, you'll end up exactly where you left off. So we go theta degrees first, and then from assuming that's the starting point, then we rotate 360 degrees all the way till we get right back to where we were before. I know that's kind of confusing to have to rotate counterclockwise first, but we're assuming that theta is a positive angle. So we rotate a positive angle, then we have to subtract 360. So we start from here and we go all the way back to where we started. Regardless, you can see that we have the same reference triangle, so secant theta minus 360 is equal to secant theta. They're the same thing. It's the same reference triangle. And these are just some examples. I just chose secant and sine as an example. But it doesn't matter if you're adding 360 or subtracting 360, you get coterminal angles. So you can see that you just get the same function. You don't have to worry about sign changes or anything like that. So go ahead and take a screenshot or a picture of your phone of these identities. Now notice at the right we're adding or subtracting 180. Now this is a little bit more involved, but it's still very easy to understand. We have analyzed this situation a bit when it comes to the tangent and cotangent functions, but now we're going to see what happens when it comes to all of the 6 functions. So ignore the pink arrows and look at this green theta here. You see that green theta here? Isn't it true that cosine, just using cosine as an example, we could use any of the functions, but cosine theta is the adjacent side over the hypotenuse. Isn't that true? So it's the adjacent side over the hypotenuse. Now let's rotate theta degrees, and then let's rotate a further 180 degrees. So theta degrees plus a further 180 degrees. That pink angle with the arrows is theta plus 180. The important thing to understand is that because we rotated from here to here 180 degrees, this line is it's a straight line. It looks like a straight line because it is. It's a straight line. Now, to make things simpler, I'm going to erase the vertical axis. Do you know that we don't even need the vertical axis to analyze trigonometric functions? The only benefit of the vertical axis is to know where 90 degrees or 270 degrees is, but remember the reference angle is determined by the x-axis and the terminal side of the angle in question. It's not determined by the vertical axis, so we don't really need the vertical axis. So that just makes things easier to see. So again, this is a straight line, and of course the horizontal axis is a straight line. Now think about this. You have two straight lines, and in my geometry course we learned the vertical angles theorem, also called the opposite angles theorem. What does that tell you? It tells you that vertical angles are congruent. So if this angle is theta, then that means that this angle is theta also. Now here's the big question. Who cares? What's the point? Well, as you know, this is the reference angle for any function with that theta value. This over here is the reference angle for the angle theta plus 180. The reference angles determine everything. So because these reference angles are the same, that means we can come up with some convenient equations. Now, cosine theta, as I said, is adjacent over hypotenuse, x over r. But look over here. Cosine theta plus 180, if you follow that pink curve, cosine theta plus 180 is negative x over r. So they're almost equal to each other, but they're not quite, because x over r over here is positive. That's the green angle. And over here we have negative x over r. So that's negative. That's the pink angle, using this red angle, of course, as the reference angle. Again, the reference angles are the same. So what that means is cosine theta plus 180 is not equal to cosine theta. But if we just write this negative symbol to change the sign, then they are equal. Because again, cosine theta is the yellow x over r. If you put a negative in front of it, then when you find the blue cosine theta plus 180, which is negative x over r, they're now going to be equal. So this also works when you're subtracting 180 degrees. You can look at this example. So that is a little bit more complicated to understand. And to be honest with you, most students and even most teachers don't really think about it. They just memorize the formulas. So I'm going to give you one more chance to take a screenshot or take a picture of these formulas. And notice that sometimes we have to have a sign change, but other times we don't with cotangent and tangent. Remember, we learned that in previous classes, that cotangent and tangent, they retain the same sign when you rotate 180 degrees and skip quadrants. So let's do some practice problems. We're going to prove that this equation is true. So cosecant theta minus 180 is equal to negative cosecant theta. If you have your equations right in front of you, you know that. And of course we divide and we get negative 1. So that was pretty easy. We proved it. Okay, let's try number 10. Tangent A plus 3 tangent A is 4 tangent A, but that's not good enough. We have to change it so that it's tangent A plus 360. And remember, when you're adding 360, it's just a coterminal angle, so you can just change tangent A to tangent A plus 360. That's completely legal. And therefore, we proved that the identity is true, but we had to go right to left in our equations in that particular example. Okay, so now we have cotangent omega plus 180. Remember, cotangent doesn't really change when you add 180 to the angle. And cotangent doesn't change when no function really changes when you add or subtract 360 to the angle. So that just stays cotangent omega. So now we're going to add these two cotangents in the numerator. And we get 2 cotangent omega divided by cotangent squared omega. And just to be clear, I'm going to factor the denominator to cotangent omega times cotangent omega. And you see that 2 of these cotangents are going to cancel out, and we're left with 2 over cotangent omega. And I'm going to make a little more room here. And then we can just bring that cotangent up to 2 tangent omega, and you see that we've proved the identity, and that was a reciprocal identity. So there you go. All right, let's try one more of these. So sine is going to change. It's going to change to a negative sine b if you're looking at your identities. And if you add those up, you get 0. So that was a pretty easy one. Okay, go ahead and try number 13. And when you come back, we'll do it together. Okay, we're back. When you add 360, it doesn't really change the function much. The value doesn't change. And when you subtract 360, the value doesn't change either. So 4 cosine alphas plus 2 cosine alphas is 6 cosine alphas. So if you got that one right, good. Go ahead and try number 14. And when you come back, we'll do it together. Okay, we're back. So secant, when you subtract 180 or add 180, it changes to negative secant. So we have negative secant over negative secant, beta is equal to 1. So that was a pretty easy one. If you got that right, excellent. Go ahead and try number 15. And when you come back, we'll do it together. Okay, we're back. So when you add 180 to the angle and tangent, it doesn't really change the value of the function. It's just equal to tangent x. And when you subtract 360, that doesn't change the value of the function either. So just to be clear what exactly is happening here, I'm going to factor the denominator. You don't have to factor the denominator, but by factoring the denominator we can see that 2 of those tangents cancel out and we have 1 over tangent x. And we now are going to use a reciprocal identity, of course, and we get cotangent x. So if you got that one right, perfect. Go ahead and try number 16, and when you come back, we'll do it together. Okay, we're back. So there's a number of different ways you can do this. When you subtract 180 from the angle in cosecant, it makes the the cosecant value negative, or you can just change it to negative cosecant A. That's a double negative. So we have cosecant A plus cosecant A, which is 2 cosecant A. And remember, you can always change that to a coterminal angle. If you want a coterminal angle, and whoops, that should be an A there, sorry about that. If you want a coterminal angle, you can just subtract 360 or you can add 360, but of course in this case we're going to subtract it so it looks like the other side of the equation. So if you got that one right, good. Sorry about the wrong angle symbol there. Okay, so now we're going to do something that's very similar, but it's actually quite different. It looks similar, but it's quite different. Instead of adding 360 to theta or subtracting 360 from theta, what we're going to do is we're going to subtract theta from 360. And we're going to subtract theta from 180. And you're probably thinking, well, what's the difference? It's the same thing. Well, actually, it's not the same thing. In this case, what we have to do, and by the way, why don't you go ahead and take a picture with your phone of these. You're going to need these. What we need to do is the 360 comes first. So you have to rotate 360 degrees all the way around, of course starting on the positive part of the x-axis. You always start in the positive part of the x-axis. Rotate all the way around, then you're going to subtract theta. So rotate all the way around, then subtract theta. Now if you subtract theta, you then have to go in the opposite direction to here. So again, we go all the way around 360, and then we go backwards to here, and that's how we get there. So the total pink angle is 360 minus theta. That's where we actually end up. So cotangent, using cotangent as an example, cotangent 360 minus theta is just this, we're going to use this reference angle, and it's x over negative y, adjacent over hypotenuse. So that's the blue down here. Now cotangent theta, notice it's a positive theta. So what you're doing is you're analyzing the triangle up here when theta is positive. And in that case, you have positive x over positive y. It doesn't say anywhere here about a negative theta. It says positive theta. So that means you're in the first quadrant, not the fourth quadrant. In fact, you're comparing all of these expressions to trigonometric functions in the first quadrant. That's what this means. Sine theta, cosine theta, if you assume that theta is a acute angle, which of course it is in this example. So cosine theta, or cotangent theta, is positive x over positive y. So they're not equal, because one of them is x over negative y, and the other one is x over positive y. So what do? You just put a negative right in front. And I forgot to show you, this is the first quadrant, cotangent theta. Again, assuming theta is an acute angle. So that's just a brief explanation of why some of those equations are true. Now, we have 180 minus theta also. So again, because the 180 comes first, you're going to rotate 180 degrees. Then you're going to subtract theta and go up this green theta, and you're going to end up here. So 180 degrees, then go backwards and end up here. I know that this is very confusing, But all you have to do is memorize those formulas. And if you don't want to memorize those formulas, we're going to learn some easier ways to remember how to recall those formulas. So that pink angle is 180 minus theta. So cosecant, for example, using cosecant as an example, cosecant of that pink angle is the hypotenuse divided by the opposite side. If you compare that to cosecant theta, assuming theta is acute, it would be in the first quadrant, and you also get r over positive y, which means that they are equal. So that's how you figure out these formulas. The difference is you rotate 360 first, then you go backwards. Counterclockwise 360 or 180, and then you go clockwise in the reverse direction because you're subtracting theta. So it's all about the reference angle. The reference angle is that green theta. So again, I know this stuff is fairly confusing. If you're thinking, I don't know if I really understand this, well, you're only required to memorize these formulas. And remember, I should be absolutely clear. If I took 1,000 students in high school or college and asked them to explain these things to me, most of them could not do it. And even most math high school teachers probably could not do it without thinking about it for quite a while. So these are not things that you're going to need to know. You're not going to need to explain them if they're a little confusing, because as you can see, this type of math is it's really digging deep into the meaning of trigonometry. And as we learned when we studied angles greater than 90 degrees, the trigonometry becomes pretty confusing. It's not exactly something that's obvious. So you're only required to really memorize those formulas. But again, I'm going to show you some easier ways to derive the formulas as we go along. So sine 360 minus theta is negative sine theta. Negative 1 plus 2 is 1. Alright. So let's try another one of these. Cosine 360 minus b is just cosine b. You don't have to worry about changing the sign. And cosine 180 minus b is negative cosine b. So you do have to change the sign on that one. And again, if you want to be able to recall these without memorizing the formulas, you just rotate. For example, on this one, you'd rotate 180 degrees and then go back to get your reference triangle, and then you would just compare that triangle to the corresponding triangle in the first quadrant. If we consider this to be beta and this to be 180 minus beta, what is the difference? The difference is this side is positive and this side is negative. Positive and this side is negative. So that's why a negative pops out. You have to multiply by negative in order for those functions or those expressions to be equal. Again, this is very advanced trigonometry. But again, you're not required to know the explanations. You're only required to be able to do the problems. So memorize those formulas and you'll be fine. So secant, if you look at your formulas, secant 180 minus theta, or 180 minus a, is equal to negative secant a. And so we get 4 secant a minus 3 secant a, which is just secant a And remember, secant A is the same thing as secant 360 minus A. So I went backwards in that particular example. I looked at my identity and I went from right to left rather than left to right in the last step. Okay, let's do one more of these before you try one on your own. Cosine 360 minus alpha. That's just going to be cosine alpha. Again, you rotate all the way around 360 degrees first, and then you go backwards. So you get a triangle here, but how does that compare to the triangle in first quadrant? Well, both these sides are positive. So cosine is going to be positive in both cases. I know those triangles are kind of warped. Sine 180 minus alpha, that's going to be equal to sine alpha. So that's a ratio identity. So that becomes cotangent alpha. Okay, so I want you to try number 21. I'm going to give you one more chance to take a picture of these identities. Take a picture, or do number 21, and when you come back, we'll do it together. Okay, we're back. So sine 360 degrees minus beta is the same thing as negative sine beta, and cosine 180 degrees minus beta is the same thing as negative cosine beta. The negatives cancel out, and of course we have a ratio identity here, so we get tangent beta. Okay, so if you got that one right, good job. Try number 22. When you come back, we'll do it together. Okay, we're back. So cosecant 360 degrees minus omega is negative cosecant omega. Add those up and you get 0. So if you got that one right, good. Go ahead and try number 23, and when you come back, we'll do it together. Okay, we're back. So you want to compare cotangent x to cotangent 180 minus x. Cotangent x, assuming x is acute, would be positive. It's positive adjacent side divided by the positive opposite side. But 180 minus x, that would be rotating 180 degrees and then subtracting x. So you get a triangle that looks like that. In that case, cotangent is going to be negative x over y, and so it's going to be negative, so it's a different sign. So we're going to get, we need to write a negative in front there so that we see that we're modifying this in order for them to be equivalent. And 360 minus x, we're also going to have to modify the sign there. So that's going to be negative cotangent x. And that's a double negative, so it becomes positive. and we get 0, which proves the equation. So if you got that one right, good job. Go ahead and try number 24, and when you come back, we'll do it together. Okay, we're back. Sine 360 degrees minus y. That's going to be negative sine y. And negative sine y plus negative sine y is negative 2 sine y. And we can change that to negative 2 sine 180 degrees minus y. If you have those equations in front of you, you see that that works. But in that case, we were going right to left. Alright, so if you got that one right, good job. So now we are going to learn the quarter rotation identities. Go ahead and get a screenshot of these equations. Now I want you to be aware that the explanations that we can give for these identities are going to be pretty complicated. When you try to combine the major concepts regarding reference angles and triangles and moving triangles in the different quadrants, it can be pretty challenging understanding why exactly these identities work. Now, you are perfectly capable of understanding the explanations, but to be honest with you, most students just want to memorize these formulas, and I am going to show you an easier way to understand why these identities work. If I chose 1,000 high school math teachers at random, I would be shocked if one of them could draw a picture like this and explain to me why these identities work. It's not that people can't do it, it's just that they choose not to do it because it's not something that is exactly easy to explain. But I'm going to go into this a little bit, and I'm not going to spend a lot of time on it because, again, you're probably going to choose to use easier methods to remember these identities. One way is just memorization, another way is using the sum and difference formulas. But let's just quickly go over the explanations for those identities. Let's say that you rotate theta degrees, but then you rotate another 90 degrees. You see this 90-degree angle here? So we're going to rotate theta degrees, and then we're going to rotate another 90 degrees. So that would be theta plus 90. That's the pink angle, theta plus 90. Now, I want you to notice something very important. A half rotation is from the positive part of the x-axis all the way to the negative part of the x-axis. That's 180 degrees, right? Now, what if you subtract the 90-degree angle from that 180 degrees? So you have a half rotation, and then you subtract this this green 90-degree angle. Well, what are you left with? You're left with alpha and theta. Now think about this. This is a 180-degree rotation. If you subtract 90 from that 180-degree rotation, you subtract 90, you're left with, again, alpha and theta. Another way to think about it is if you add theta and 90 and alpha, then you get 180 degrees. Add theta, 90, and alpha, and you get a half rotation, which is 180 degrees. So we're adding theta, alpha, and 90. But if you subtract 90 from both sides of this equation, then you can see that alpha and theta are complementary angles. Remember, complementary angles are angles that add up to 90 degrees. The big question, obviously, is who cares? The reason that we care is because both theta and alpha are reference angles. The fact that those reference angles, and by the way, theta is the reference angle for the green theta angle, and alpha is the reference angle for the angle theta plus 90. What we're trying to do is come up with formulas that relate the trigonometric functions for these two angles, theta and theta plus 90. But alpha is the reference angle for the theta plus 90 angle measure. Now, because alpha and theta are complementary, you can come up with all kinds of interesting equations. So what I'm going to do is I'm going to take this triangle out, and I'm going to put it down here. And now that we know that theta, the green theta, and the orange alpha are complementary angles, we need to make a very important discovery here, so to speak. In any right triangle, this angle and this angle must add up to 100, or they must add up to 90 degrees. This angle and this angle must add up to 90 degrees. Do you see why that is? Remember, we learned in my geometry course that the sum of all three angles in a triangle is always 180 degrees, right? We learned that in my geometry course. If you add up all the interior angles, there's always 3 total. In a triangle, you always get 180 degrees. But think about this. We know that in a right triangle, this is a right triangle, one of the angles must be 90 degrees. So what that means is that these two angles must add up to 90 degrees. Because, again, the sum must be 180. So when you subtract this right angle from 180, you're left with a total of 90 degrees left for these two remaining angles, which means they must add up to 90 degrees. Again, the big question is, who cares? What's the point? Well, isn't it true that sine alpha is y over r, right? But cosine theta is also y over r. So if you rotate theta plus 90 degrees, sine theta plus 90 is y over r. But cosine of that green angle, and if we take out this triangle over here and write it, whoops. Now again, you don't have to know this explanation. If you're getting a little confused here, that's okay. You don't have to know this. I'm just giving you a brief explanation of why this works. If we take that angle out, cosine theta, and again, in both of these triangles, we have alpha and theta. So up here we have alpha in that angle. Cosine theta is equal to the adjacent side over the hypotenuse, and the ratio of those two sides, because these two triangles are the same shape, the ratio is also going to be y over r. Another way to think about it is to go over here and think cosine theta is y over r. Now again, that's a lot to think about. That's a lot to take in. Especially given the fact that we don't really know the lengths of the sides. We only know the ratios of the sides. Long story short, sine theta plus 90 is equal to cosine theta. And again, I'm not going to spend a lot of time explaining this because most students don't really want to know it. Another situation is when your 90-degree angle is cut by the x-axis. In that situation, your reference angles, in this case the purple omega and the orange alpha, they must be again complementary angles, because if you cut right through that 90-degree angle, then obviously the purple omega plus the orange alpha is going to be 90 degrees. So again, you have the same situation where you have a pair of complementary angles. So the most important thing to notice about these identities is that you're changing from one function to another function. We haven't done that yet. In every identity that we learned, we went from, we stuck with the same function. Here we're changing functions. So whenever you have a 90-degree angle in these identities, you're actually changing you're changing to a different function. So be sure to take a picture of these. I'm going to show you an easier way to remember these identities. Here's some other identities. We have 90 minus theta. These identities are a little bit different. Be sure to get a picture with your phone of these. And be aware that here we have the negatives on top. So when you have an addition sign here, it's a negative sign. And when you have a negative sign here, it's an addition sign. So those are reversed. These are not reversed, so be careful about that. Okay, so let's do some practice problems. Okay, so if you have your screenshots, sine theta plus 90 is equal to cosine theta. So it changed to a completely different function. And sine theta minus 90 is equal to negative cosine theta. So we have a double negative. And we get 2 cosine theta. So again, most people just memorize these identities. But if you forget the identities, again, we're going to learn the sum and difference methods for finding the values of these identities or deriving these equations. Let's try number 26. Cotangent A minus 90 degrees is negative tangent A. Again, you should have these formulas right in front of you. Multiply these together and we get negative tangent squared A. So let's do a couple more of these before you try one on your own. Cosine 90 minus theta, or 90 minus B, is equal to sine. So that just becomes sine squared B. And secant 90 minus B is equal to cosecant B. Again, notice that we're changing to completely different functions. Whenever you have a 90-degree measure there inside your composite expression for the angle, you're going to change to a completely different function. But only when you have 90 degrees. When you have 180 or 360 in all these formulas, you're going to keep the same function. So now we're going to use a reciprocal identity. So then we have sine squared b over sine b, and just to make things absolutely clear, you don't have to do this, but if we factor the numerator, you can see that one of those sine b's cancels out. So sine squared b is the same thing as sine b times sine b, and again, one of those sines cancels out, and you're left with sine b. So we proved it. We did it. Okay, so on to number 28. Cosecant 90 minus omega is secant omega. And we know from our Pythagorean identities that secant squared omega is tangent squared omega plus 1. And there you go. So I want you to take a screenshot. I'm going to give you one more opportunity to take a picture of these quarter rotation identities. And I want you to take a picture of both these pages, because we have other identities here. And remember, when you're subtracting theta from 90, that's very different from adding 90 to theta or subtracting 90 from theta. So just be aware of that. I know that's kind of confusing to think about that. Okay, so I want you to try number 90 and or excuse me, try 29, and when you come back, we'll do it together. Okay, we're back. So cosine 90 degrees minus alpha, that switches to the sine function, and cosine alpha plus 90 is negative sine alpha, and of course when you add those you get 0. So if you got that right, excellent. Go ahead and try number 30, and when you come back we'll do it together. Okay, we're back. Sine x plus 90 is cosine x, and cosine x minus 90 is sine x. And now we can use a ratio identity, of course, and we get cotangent x So if you got that one right, perfect. Go ahead and try number 31. When you come back, we'll do it together. Okay, we're back. Cotangent A minus 90 is negative tangent. But before we do that, let's change the form of this because it can get a little confusing with that square. So these two expressions mean the exact same thing. The difference is this mint green expression is a little bit easier to understand. Now cotangent A minus 90 degrees is, like I said, negative tangent A. And when you square that negative tangent, you're just multiplying negative tangent A by itself. And of course you get tangent squared a plus 1. And we know from our Pythagorean identities that that is equal to secant squared a. So if you got that one right, perfect. Good job. All right, go ahead and try number 32, and when you come back, we'll do it together. Okay, we're back. Tangent 90 minus b is equal to cotangent, so that converts to cotangent cubed b. So again, this here changed to that, and now we can multiply those together, and we get cotangent to the 4th power b. So if you got that right, excellent. Okay, so as you can imagine, it's pretty challenging to have to remember all of these formulas. If you can conceptualize these explanations, then you don't really have to memorize them. But to be honest with you, that's a pretty daunting task for most students to understand this stuff on that level, because most math teachers don't understand this stuff on that level because they're just not required to. It's easier to just memorize the formulas. Again, with these identities, you can remember them just by understanding these explanations, because these identities work for any value of theta. So if you can show that one of these equations works for one value of theta, whether it be an acute theta, an obtuse theta, or a reflex theta, then it's going to work for every theta. So if you can understand these explanations on some level with some example theta value, whether it be acute, obtuse, or reflex, then you don't have to remember these formulas. But and the same is true for these. But you have to start with a 360-degree angle, rotate all the way around, then subtract and go the other way to get your reference triangle. That can be a little confusing for students. With 180, you do the same thing. You rotate all the way around, and then you go backwards because you're subtracting, and that gives you your reference triangle. But when you get to the quarter rotation identities, things can get really difficult really fast. The explanations are not very simple. So instead of having to know any of those explanations, you can retreat, so to speak, to the sum and difference formulas. If we want to prove that this is true, let's say that we just want to find what that value is equal to, then we can use a sum formula, because we are finding the sine of the sum of two angle measures, but that's exactly what our sum formula tells us to do, or it shows us how to do it. So we're going to derive this identity. Let's say that we're trying to figure out what sine theta plus 90 is equal to, but we don't know. Let's say we forgot that it's equal to cosine theta. So we're going to start with this formula, but instead of A, we're going to plug in theta, and instead of B, we're going to plug in 90 degrees. So now we have sine theta times cosine 90 degrees plus sine 90 degrees times cosine theta. Now we have to go to our curves. Now remember, the cosine curve looks like this. At 90 degrees, the cosine curve is actually 0. The cosine curve is that green part there. It's right where it crosses the x-axis. At 90 degrees, it's 0. So again, you can look at those curves. Whenever you have a quadrantal angle or a collapsed triangle, you want to use your curves. We have the sine curve, 90 degrees, 180 degrees, 270, and 360. And these highest points have y values of 1. The lowest values have y values of -1. You should be fairly familiar with this at this point. Your cosine curve looks exactly like the sine curve, but we have 90, 180, 270, and 360. Anyway, at 90 degrees, the cosine value is 0. So we have sine theta, and we'll use parentheses just to avoid any confusion, times 0. Now sine 90 degrees, that's 1. That's up here. That's 90 degrees there. That's 1. So that just becomes 1. And so we have 0 plus cosine theta, and we did it. If you need to know what sine theta plus 90 degrees is, you can use this formula and that'll tell you. And the same is true for every single formula that we used. You can either use the sine of a sum of two angle measures, the sine of the difference of two angle measures, or the cosine of a sum or the cosine of a difference. Okay, so let's try the next problem here. We want to prove that this identity is true, or derive that equation, so to speak. But we don't have a formula for the difference of two angle measures for the secant function, so we're going to have to convert to the cosine function using a reciprocal identity. And so now we do know cosine a minus b, that is this expression here. So I'm going to give you these expressions so you don't have to go back to your notes and find those, but let's go ahead and do this. So we want to find secant 180 degrees minus x. So a is going to be 180, b is going to be x. So we get 1 over cosine 180 degrees minus x, and that is going to be cosine 180 degrees times cosine x plus sine 180 degrees times sine x. Now, if you look at your cosine curve, we have 90 degrees and 180 degrees. That's at -1. So that's -1. Cosine 180 degrees is -1. So I'm going to use parentheses just to avoid confusion. Now sine 180 degrees, if you look at your sine curve, that's going to be 0. So we go out 90 degrees and 180 degrees, 270, 360. So right in the middle is 180. That's 0. So sine 180 degrees is 0. And again, you can use this method to derive every formula that we did today. So we end up with 1 over negative cosine x. And let's find a little bit more room. So the final solution, using a reciprocal identity, we can make that negative secant x. So we did it. So if I forget this identity, I can use the cosine of a difference of angle measures to help me actually derive that. If you are taking a test and you forget, you can always use the sum or difference formulas. So let's try one more of these. So we're going to show that this equation is true. We're going to prove that it's true using the difference formula. But we don't have a difference formula for tangent, at least not one that we can easily recall. But remember, tangent is sine over cosine, so we're using a ratio identity. And we know the sine of a difference of two angles and the cosine of a difference of two angles. So if we're trying to find tangent 90 degrees minus omega, that's equal to sine 90 degrees minus omega over cosine 90 degrees minus omega. And we can just plug in, so sine 90 degrees times cosine omega minus sine omega times cosine 90 degrees all over cosine 90 degrees times cosine omega plus sine 90 degrees sine omega, and sine 90, well, look at your sine curve. In 90 degrees, sine is 1, and cosine 90, that's going to be here on your cosine curve. Cosine 90 is 0 if you have that curve right in front of you. So we already found cosine 90 is 0. We already found that sine 90 is 1. So we have cosine omega minus 0 over 0 plus sine omega. Let's find a little more room here. And then we have cosine omega over sine omega. Sorry, we're running out of room. And of course, that's a ratio identity. That's equal to cotangent omega. So we proved it. We found what that equals just by using a difference formula. Okay, so I want you to take pictures of 33 and 34, and you can try number 36. I've got the difference formula for cosine written for you, so you can use that formula to show that this identity is true. Go ahead and try number 36. This is how you can remember these identities, or rather, it's what you do if you cannot remember the identities. So try 36. When you come back, we'll do it together. Okay, we're back. So cosine 90 degrees minus alpha is equal to cosine 90 degrees times cosine alpha plus sine 90 degrees times sine alpha. Now cosine 90 degrees, if you have your cosine graph in front of you, you know that that's 0. Sine 90 is 1. So we have 0 plus sine alpha, which of course is equal to sine alpha, so we proved it. If I forget this formula, I can always use this difference identity to actually derive the formula on my own. That's a powerful tool. A tedious tool, but a powerful tool. Try number 37. And when you come back, we'll do it together. Okay, we're back. So we want to find cosecant beta plus 180 degrees, and let's say that we forgot what that is. Let's say that we don't know it's negative cosecant beta. So we're going to use a reciprocal identity. And then we're going to use the sum formula for the sine function. So cosine 180 degrees, that is equal to -1. How do I know that? Well, you got to look at your cosine curve. That's a quadrantal angle, meaning it's a collapsed triangle. So your cosine curve looks something like that. At 180 degrees, we have 90 degrees, then 180, then 270, and then 360. That's how that works. So that would be -1. Make sure you write parentheses on both the sine beta and the -1 to avoid confusion. Now sine 180 degrees, that's going to be 0. We have 90 degrees and then 180 degrees, it's 0. And again, write parentheses to avoid confusion. So now we have 1 over negative sine beta plus 0, which is 1, well, we can say -1 over sine beta. And let me find some more room here. Sorry, this is scrunched in like that. And we can use a reciprocal identity that now becomes negative cosecant beta. So we proved that that identity is true, and let's say we forgot that cosecant beta plus 180 is negative cosecant beta. We could use this formula to help us remember. Again, that's a powerful tool. So if you got that one right, perfect. Let's try one more problem today. Attempt number 38, and when you come back, we'll do it together. Okay, we're back. So we're trying to find cotangent theta plus 90 degrees, which is cosine theta plus 90 degrees over sine theta plus 90 degrees. So we have cosine theta times cosine 90 minus sine theta times sine 90 all over sine theta times cosine 90 plus sine 90 times cosine theta. So if we look at our curves again, cosine 90 degrees is actually 0 if you look on that curve. So we have cosine theta times 0, use parentheses to avoid confusion, and sine 90 is 1. Again, that's here. Sine 90 is 1. Remember, these functions go up and down between -1 and 1. the sine function and the cosine function, that is. Now, cosine 90 degrees, we already found that that's 0, plus sine 90 we found is 1, so plus 1 times cosine theta, and we have negative sine theta over cosine theta, which is equal to negative tangent theta. That is a ratio identity. So if you got that one right, excellent. Okay. We're not going to do problems relating to these formulas here, but these formulas technically are something that you could see. Now, the chance of you being required to do these formulas is so low that I'm not going to really spend any time covering these, because it's going to take away the focus from other formulas that are actually used frequently in upper mathematics. But the last grouping of identities that we're going to learn are the product to sum formulas and the sum to product formulas. Now, one reason that we're not going to go over this in detail is that these formulas can actually be derived. And so if you need to use them, you can just create them on your own. So what we're going to do now is we're going to derive the first formula. And again, you're not going to use these really in upper mathematics, so that's why we're not really going to go into this much. But you know the sign of the sum of two angle measures and the sign of the difference of two angle measures. Again, those are the sum and difference formulas for sine. Well, it turns out that if you add those together, you can see over here this pink formula comes from here, and the orange formula comes from here. But notice that there's like terms. This term here and this term are like terms, and one is positive and the other is negative, so they cancel out. Also, these terms are like terms, but they don't cancel out, so you can add them together and you get 2 sine A cosine B. If you then divide both sides of the equation by 2, you can write this over 2, or you can simply write times 1/2. Times 1/2 and over 2 are the same thing. So that is the product to sum formula. You have a product and you're converting to a sum. So as you can see, they're fairly easily derived. For this formula, you just subtract instead of adding. And for cosine, the cosine equivalents, you add the cosine and subtract the cosine formulas to derive those. So if you need to come up with those formulas, that's how you can derive those. And we may do some problems where I'll ask you to derive those formulas, but we're not going to do a lot of practice problems with those, because again, they're just not really necessary. Now, you can also create sum to product formulas. So we're going to write the same formula where we add the sum formula and the difference formula, and we get this expression here. So we're starting where we left off in the second stage here. We added those together, those two terms canceled out, and we're left with this. We're going to take that over here, and we are going to replace A with A plus B over 2 in the blue, and we're going to replace b with a minus b over 2 in the yellow. Now, why in the world would we do that? Well, when we add these, we come up with sine A. And if we add these, we come up with sine B. So now we have the sum of sine A and sine B, which is equal to this expression over here. So we call this a sum to product formula. We're starting with a sum and going to a product. And so that's another way of writing these. Now again, you might wonder, can we just plug in a plus b over 2 for a? Is that legal? And the answer is yes, it is legal. You can plug in anything into the formula as long as it's a real number and not some imaginary number. So this formula is the same formula that we have over here. The only difference is you're looking at it in a different way. So you may see these formulas. There's a chance, there's a probability, but that probability is so remote that I'm not going to waste your time making you do these types of problems. I just want you to be familiar with the derivation of these problems. Now, the derivation of the identities. The derivation of the product of sum formulas is fairly easy, but you probably are kind of wondering, how am I going to remember this thing here? Well, again, it's not that important. So I just wanted you to see the derivation of these formulas briefly. Again, I hesitate to even show you these formulas because they're just not used enough to really justify any time studying these. But again, the good news is you can derive these formulas if you want to practice deriving those, and I will probably give you a few problems guiding you along, showing you how to derive these formulas. But I'm going to make the problems very easy because, again, I don't want to spend a lot of time on these identities, these equations. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5 and number 6, number 7, number 8, number 9, and number 10. But don't go before you get your homework. Here's the homework. Get a picture of these first couple pages, and the 3rd and 4th page, and the next pages. But don't go before you get the answers. Let's take a look at the answers to the homework. So here's the answers for 1 through 8. And the answers for 9 through 16. And 17 through 19. And number 20. So get that homework done completely correctly and neatly and keep it in order in your binder. Remember, if you don't do the homework, it's a 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.